What's going on, guys? Welcome to my video about Transformer XL. In today's video, I'll be discussing Lil'Log's blog post, and you'll learn the differences in architecture between the vanilla transformer and the iterated Transformer XL, which in essence increases the context of a vanilla transformer. So what are we trying to solve with this new architecture? In a vanilla transformer, when the input shifts, that is to say, when a new token is generated, the entire segment or sequence, so these two terms are interchangeable. Segment is used in the Transformer XL paper though, which is worth noting. You must reprocess the entire segment from scratch in that context window, even though the n-1 tokens overlap from the previous token generation. But as vanilla transformers are designed, they cannot take advantage of this. And therefore, we lose this context from the previous segments, which is important to understanding the current one. What is Transformer XL proposing? It gives a mechanism to reuse the hidden states from previous segments, which is helpful to think of as a recurrent connection across multiple segments. So that's a quick introduction. Let me just get back to the problem through this diagram, which is very helpful on the top right corner. And this shows how training occurs, or evaluation, sorry, in a vanilla transformer. So in our first segment from X1 to X4, this is also masked attention, by the way. You can tell that it's masked attention since the attention links are only from a token backwards. So there's no attention connecting X1 to X2, for example. And these are the hidden states. So we can use X1 to X4 to calculate X5 here. However, when we go calculate X6, we lose the context from X1. And furthermore, when we want to calculate X7 in the top right corner here, then we lose the context from the first two tokens. So this is the issue of the limited context. And the Transformer XL reuses the hidden states, which you can also think of as intermediate representations from the previous segments as additional context for the next one. And this is very important, in particular, for capturing the long-range dependencies. So if we scroll up here, I'll explain what we have going on. So I mentioned hidden state, but what does that mean exactly? So the hidden state at layer n reflects the token's context after applying multi-head self-attention and feed-forward transformers up to that layer. So if we look at these two diagrams, we have our segment 1, which is 4 tokens in length, and each hidden state, so we have hidden state 1, 2, and 3, so there's 3 hidden states in this, represents one pass through attention, multi-head attention, and one pass through a point-wise, fully connected feed-forward neural network. So there's 3 passes here, and this is encoding the context from the surrounding tokens through each pass. And each pass better captures the relationship between the tokens and their context. And whereas in the vanilla transformer, as you can see, we discard the hidden states from one segment to the next, in Transformer XL, hidden states from previous segments are stored and reused. And it, in essence, creates a memory that spans segments, allowing the model to maintain a connection between past and current ones. So in the example here, we are maintaining a one segment memory, and you can see this is done through the concatenation operation from segment tau to segment tau plus 1. But more on that later. Let's look at this diagram once again. And this is pretty simple. In a vanilla transformer, we consider the segments discretely, whereas in the Transformer XL, when we're training our new segment, we account for these hidden states as we calculate the next token. And remember, we're not doing back propagation to these layers. So if you're doing training on a Transformer XL model, you'll need to do requires grad equals false, so that you don't accumulate any gradients, because you're just using the context. This is only done for the forward pass and not the backward pass. Okay, now let's parse what's said in this paragraph. So we're going to label a hidden state of the nth layer for the tau plus 1th segment. So what this is saying is that, let's say segment 2 is tau plus 1, and we label the nth layer. So if n is 1, then we would have segment 2, layer 1 as this. So h of, in our example, segment layer 1 and segment tau plus 1 equals 2. In addition to the hidden state of the last layer for the same segment. So in this case, the hidden state is in fact the segment itself. So that's just the initial embedding. However, this is the same setup as the vanilla transformer, which is to say that the future hidden state depends on the previous one, which is an extremely evident statement. This is saying that the previous encoding that was calculated using a multi-head attention as well as a point-wise fully connected feed-forward neural network is input to the next transformer block, which produces the next hidden state, or in another way, the future sequence is a function of the previous one. However, we also preserve the lateral dependency. So let's see what they say here. It also depends on the hidden state of the same layer for the previous segment, h tau equals 1 of n, which is still hidden state 1. So what we're saying is that this hidden state is dependent, of course, on the token embedding, but also on the n equals 1 hidden state of the segment, which is one segment behind. And by incorporating information from the previous hidden states, the Transformer XL model extends the attention span much longer over multiple segments, because although the direct context is from these tokens, of course, these tokens have an embedding from the previous segment as well. So there is some implicit context happening here. And I'll also mention that you can expand this. So you can add 2 segments. There's no limit. Of course, there will be drawbacks. At a certain point, returns will be diminished. But in our example here, we're simply adding 1 segment. And let's go through and parse this. So first of all, everything that's red is what's changed from vanilla transformers to Transformer XL. So when we calculate our hidden state, it's H tilde. And what we do is that we take our normal calculation here. So this is the hidden state itself, and add the hidden state from the previous segment at the same layer. So that would be this one. So we concatenate this segment and this segment. And it's important to note that the concatenation operation is along the sequence length dimension. So what that means is that we don't concatenate them like this, like one on top of the other. We're connecting them in this way, okay? Furthermore, the query matrix is the only one of the 3 in our attention calculation which is the same. And this is because the encoder is what imbues or bakes in the representation of the input for the decoder to get the next token. So it doesn't make sense to give the decoder previous states when the encoder's role is already to get the context within this representation. So this is the reason why we only perform the addition of the hidden states on the key and value matrix. So once again, we concatenate to get H tilde with the previous segment that is also stop gradiented so that we don't accumulate any gradients. It's only used for the forward pass. I'm repeating myself. And once we have these 3 values, we simply feed it in to transformer layer, which is to say a multi-hit attention, of course, followed by add in norm. So layer norm as well as adding the recurrent connection. And then that's followed by another feed, or not another, but point-wise feed forward neural network, followed by another layer norm and add the recurrent connection. So this is the essence of the algorithm. You can read the paper if you want to get more details. But one last note is that Transformer XL needs to use relative positional encoding because previous and current segments would be assigned the same encoding if we encoded absolute positions. What this means is that the problem with absolute positional encoding is that X9 and X5, when we concatenate the hidden states, will be the same distance apart. So it's as if you have 2 words in one spot, which is impossible. And this is where you use positional encoding so that we can calculate X5 and X9 as having 3 tokens between them instead of being in the same place. So the reason why, once again, we need the relative positional encoding is because X5, X1, X2, X6, X3, X7, X4, and X8 are respectively the same distance if we use absolute positional encoding. So that was a quick recap of Transformer XL. If you'd like to learn more about different transformer architectures, I really recommend reading this blog post, and I hope you have a good day. These 2 segments for our